Side. Yeah, no, it is. But like, I just and then.
All right. Howdy, y'all. Welcome. Happy Friday afternoon, evening, whatever time 4:30 is to you. Not too much logistics to talk about. Make certain you all. So, quiz due tomorrow. If you haven't already done attempt 1, obviously, remember you get 2 attempts. Knock it out. Make yourself proud. Remember, after kind of this point, so after kind of class today is kind of where we're getting into the weekend. So if you shoot me an email, just don't expect me to respond until Monday. So that's just work life balance. Remember, I told you all that. Throughout the week, I'm on it. Respond to emails up the wazoo. But come the weekend, that's kind of work, that's family time for me. I will respond to them, but if you have questions about the quiz or anything like that, do not expect a response until Monday. I will respond on Monday. So, last class, we got into 1D kinematics a bit more. Remember, that's just 1D motion. We talked about position, we talked about displacement, we got to velocity. We said velocity is just the derivative of position with respect to time. So dx dt, bam, you get velocity. We did a couple problems with that, just some simple stuff. Average velocity is just change in position over change in time. If we want instantaneous velocity, we had to do that derivative. We talked about, okay, it is the derivative of a function is the slope of the function. So if I give you a graph and I say find the velocity at some point, and I give you a position versus time graph, the derivative of said graph, aka the slope at every single spot, gives me the velocity. So we went through that. We distinguish between velocity and speed. Velocity is how fast you're going and the direction. Speed is just how fast you're going. So 30 miles per hour east, that's velocity. 30 miles per hour, that's speed. And then we did a problem with this. Calculate the instantaneous velocity using a function where I gave you the function position. Velocity function is the derivative of that. We got the instantaneous velocity from that. We got the instantaneous speed by just taking the absolute value. And we got the average velocity 2 different ways. We got the average velocity 1 by doing the final position minus initial position over the change in time. And then we also introduced, well, average just means take if you have the 2 numbers, the average of them is add them and divide by 2. So there's kind of 2 ways to do that. All right, so today we're going to get into the last word that we need to know when it comes to 1D kinematics, which is acceleration. I mean, we need to know time, but time is a little funky thing. Most of us are pretty comfortable with time. So acceleration is the last major one. It's the rate of change of velocity. So velocity is the rate of change of position with respect to time, the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. So its derivative is all the way down. So if you take the derivative of position, you get velocity. If you take the derivative of velocity with respect to time, you get acceleration. Acceleration is not how fast you're going. One of a really common conceptual mistake people get into is acceleration is how fast you're going. Acceleration is not how fast you're going. It is whether you are speeding up, whether your velocity is increasing, whether your velocity is decreasing, and this last one is the one that throws most people off, whether your velocity is changing direction. So, acceleration is a vector. So if your velocity is changing direction, that means your velocity vector is changing, which means you are accelerating. An example of this is if you turn your car to the left. So say your car is going up. So we have to keep our mind in vector mode. So say your velocity was up, and you take a turn, and after that turn, your velocity is now to the left. You did accelerate. And then maybe like, but I didn't get faster or slower. Here's the key to that. Think of it in components terms. Think of it in terms of components. Remember, whenever we talk about vectors, we have to think about it in x and y components. If you're going up to begin with, you're all in the y direction. You're all in the y direction. All your velocities in the y direction. Well, if you're now going to the left at the end, now all your velocity is in the x direction. So if you think about it in vector terms, your y velocity went from something to nothing. And your x velocity went from nothing to something. So the components changed. So you did accelerate. Sounds weird, but we're going to see lots of examples as time goes on. If your velocity changes, you did accelerate. You didn't get faster or slower, but your direction changed. So that's a really important kind of concept to have somewhere tucked into your head. Acceleration is your change of velocity. That can mean either the amount of velocity or the direction of velocity. Okay? And then the equations here just reflect all the things I said. So the units for position were meters. Well, if we wanted velocity, was meters per second, because there was a change of distance over time. Well, now, if we have acceleration, we have the change in velocity over time, which is meters per second divided by seconds. If you simplify that, we get the units for acceleration, meters per second squared. It comes from acceleration is the change in velocity over time. So just chuck your unit for velocity there, divide it by the unit for time, and bam, meters per second squared. That's where it comes from. It comes from the logic behind it. And then here again we see the derivative. Now for one-dimensional motion, we're only going to care about the x component of velocity. When we get to two-dimensional motion, we'll care about both. So the derivative of velocity with respect to time gives us acceleration. And we can get the average velocity by just doing the change in velocity over the change in time. In the same way that the average velocity was a change in position over the change in time. So again, it's a step ladder kind of thing. Position to velocity, we do a derivative. Velocity to acceleration, another derivative. If you want to do position to acceleration, that's 2 derivatives with respect to time. And then if you want to go backwards, you do an integral. Yeah. We're going to ask, if you go backwards. Yeah, if I want to go from acceleration back to velocity, you integrate it. If I want to go from velocity back to position, I integrate that. So if you want to go all the way from acceleration all the way back to position, integrate it twice. And there'll be some examples of that as well. So, there you go. Acceleration. There it is. We're going to do some practice with it. So, let me go ahead and get this. Well, fingers crossed it didn't remember me. All right. So sad. Can I pause the stream? No. So fun. Okay. So here's the question for you all. An object starts at rest and accelerates to 12 meters per second in 4 seconds. What is the acceleration? Looks like we're going to have 2 streams. So bye, streaming people.